In this video, we're going to talk about a second definition of acids and bases called Bronsted-Lowry acids and bases. So Bronsted-Lowry acids are any compound that donate a hydrogen ion, and then Bronsted-Lowry bases are any compound that accepts the hydrogen ion. So the reason we have a second set of definitions is because the Arrhenius acids and bases definitions are a little bit restrictive. Here we have a broader definition and it includes more types of acids and bases. So here's an example of a Bronsted-Lowry acid and base reaction. When we write these reactions, we're always going to have both the acid and the base in the same reaction. With Arrhenius, we had one reaction for acids and a separate reaction for bases. Here it's all combined into one. So in this example, we have NH3 and water, and what we are making is NH4 plus and OH minus. So what we need to do to decide what's the acid and what's the base is see how things are changing. So if we look at the NH3, it is turning into NH4 plus. So to go from NH3 to NH4 plus, that has to add a hydrogen ion. If we look at the water, it's turning into hydroxide or OH minus, and to go from H2O to OH minus, you are losing the hydrogen ion. So based on our definitions, if you lose a hydrogen ion or donate the hydrogen ion, then that is the acid. So in this case, water is our Bronsted-Lowry acid, and then the NH3 is accepting or adding the hydrogen ion, so it is the base. Our Bronsted-Lowry reactions are always going to have four parts. So the reactants, one of them is going to be the acid, which is what donates the hydrogen ion. And then the second reactant has to be the base. It's accepting the hydrogen ion. So hopefully you see if something's donating, something's accepting, you have to have, if you're donating, you have to have something that's going to accept it. For the products, you're going to have a conjugate acid, which is what's produced from the original base. So it's the original base plus the H plus that it's accepted. And then we also have the conjugate base, which is produced from the original acid after it's lost the H plus. And what we have here is what we call a conjugate acid-base pair. So the acid turns into the conjugate base, and the base turns into the conjugate acid. So let's look at some examples. Here is the visual of what's actually going on. So here HCl is our acid. So it's going to donate the hydrogen. So what actually happens is the lone pair on the base makes a new bond with the hydrogen from the acid. Those electrons in this case the HCl bond, are transferred to the chloride ion. So we produce that chloride ion. We make NH4 plus. So here's our new nitrogen hydrogen bond that we made. The HCl is the acid. It's donating H plus, so minus H plus. NH3 is the base. It is adding H plus. So if I take away H plus from HCl, we're left with Cl minus. If I add H plus to NH3, we have NH4 plus. So that means the acid is turning into the conjugate base, and the base is turning into the conjugate acid. And again, the acid with the conjugate base is a conjugate acid-base pair, and the base with the acid is also a conjugate acid-base pair. So what we're going to do in this reaction is label the acid, base, conjugate acid, and conjugate base. So you're given the full reaction, you just need to see what's losing and what's gaining hydrogen ions to decide. So if we look at the first reaction, we have H2SO4 plus bromide ions, making HSO4 with a negative charge and HBr. So the H2SO4 is turning into HSO4 minus. So to do that transition, we are taking away hydrogen ions. So we're going from 2 hydrogens down to 1, and we're going from neutral to negative. Bromide is going from Br minus to HBr, so that's adding H plus. So we're adding on a hydrogen, and we're going from negative to neutral. So if that's the case, then the H2SO4, it's losing H plus or donating it. It means it's the acid. The bromine ion is adding H plus, which means it's the base. The acid turns into the conjugate base, and the base turns into the conjugate acid. Go ahead and pause the video and see if you can label the 4 pieces of the second reaction. All right, in this reaction we have NH3 turning into NH4 plus. So that's adding a hydrogen ion, which makes it the base. Then we have H3O plus turning into H2O, so that's losing the hydrogen ion, which makes it the acid. The base turns into the conjugate acid, and the acid turns into the conjugate base. So you can notice acid and base are always reactants. Conjugate acid and conjugate base are always products. In these practice examples, we're going to write the products. So in this case, I'm not telling you what's the acid or base or what the products are. So let's take a look and see if we can decide what's what. Sometimes you'll have to be told. Other times you will also be given some information. You'll have some tables that you can refer to as to what are acids and bases. But if we look at this first example, we saw this one earlier when we talked about arrhenius acids and bases. So we have this hydrogen that's attached to oxygen. So that makes this the acid. We know with Bronsted Lowry we have to have an acid and a base. So that means the water must be acting as our base. Acids, we said lose H plus. Bases, we say add or accept H plus. So if I take away H from this first reactant, we have CH3COO. It was neutral and I took away something positive, so I'm left with something negative. Water, we're adding a hydrogen ion, so we're going from H2 to H3. And we were neutral and we're adding something positive, so we're ending with something positive. The acid turns into the conjugate base, and the base turns into the conjugate acid. For the second reaction here, we have these 5 hydrogens are attached to this carbon, and that's all we have. So it cannot be the acid, which means it has to be the base. And if that's the base, then the water must be the acid. So again, base is going to accept the hydrogen ion. The acid is going to lose the hydrogen ion. So if I add a hydrogen to this formula, you could make this H6, or you could put the hydrogen on the end. Either way is fine. I went from something neutral, I added something positive to it, so I'm left with a positive charge. Water was H2, I'm taking away a hydrogen, so it's just H, and O went from neutral to a negative charge. The base turns into the conjugate acid, and the acid turns into the conjugate base. So notice in those last 2 reactions, one reaction water acted as the acid, and in the other reaction it acted as the base. So water can act as either one depending on what it is mixed with. So you can never just look at the water first and decide if it's the acid or base. You always have to look at what it's paired with. So anything that can do this, act as both an acid or a base, is called amphoteric. So water is one example of an amphoteric molecule. There are many others, but water is what we want you to connect this definition to.